Hello? Okay, so we will going we will be starting the uh, we will continue our Fourier transform properties. Uh, so uh, so far we have done two properties. We have done the uh, so far we have done the linearity. So properties of Fourier transform. The first property we did was linearity. Yeah, the linearity property. Just the voice here. Yeah. So the linearity property is the first property, which says that if there is a function x of t and the Fourier transform is x of omega, then uh, ax1 of t, the Fourier transform will be ax in the Fourier domain will be uh, ax of omega. And if there is another function bx2 of t, then the Fourier transform will be bx2 of omega. So if we add these two functions in time domain, the functions will also be added in the Fourier domain. So on the right hand side, the Fourier transform will be just the sum of the two Fourier transforms. This is the linearity. The second property is what we did was the time shifting. And the time shifting property, it says that if we shift, so if the Fourier transform of a function x of t is x of omega, this is the Fourier transform. So if we shift the function, so if we shift it right or left by an amount of t naught, so if we shift it by t naught, then the Fourier transform is, we don't need to calculate it again. We can just find the Fourier transform by uh, just copying the Fourier transform for the unshifted and multiplying it by the phasor, by just a phase, which is minus j omega t naught. So it means that the magnitude is same. Only difference is the phase. Now let us go to the third property, which is the property of. So you can look at the lectures actually, which I sent you, the 8th lecture. So I'm just following that. So the third property is the property of conjugate, the conjugate symmetry, which says that this is the third property, which is the property of conjugate symmetry. This property says that uh, if I have x of t, the Fourier transform is x of omega, then the Fourier transform of the conjugate, and x of t is complex, so the Fourier transform of the conjugate of x of t is Fourier, the conjugate of the Fourier transform. So we, on the other side, we can just take the conjugate and the negative of the frequency. Now, this property is important because this property has two more uh, results which follow from this property, and those results are more important than the property itself. And those results are that if a function x of t is a combination of even function and an odd function, if it is a combination of an even function and an odd function, like that. So if it is a combination of even and an odd function, yeah, so if it's a combination of an even and odd function, then the even function, the Fourier transform of the even function will be real of x of omega. And the Fourier transform of the odd function is imaginary of x of omega. So this is a very powerful property, and we can find Fourier transform of some other functions with that by using this property. Now let us look at an example which is given in the lecture, and that example wants us to find the Fourier transform of a double exponential, double-sided exponential. So I need the Fourier transform of this. I need to find the Fourier transform of double exponential. So this is e raised to the power minus a t. This is 1 and this is t. I need to find the Fourier transform. Now I know from my previous results that the Fourier transform of the this is an even function. This is an even function. This is an even function. I know the Fourier transform of this exponential, which is e raised to the power minus at u of t. I know the Fourier transform of this is 1 over a plus j omega, and it's a complex number. But as you can see that this is equal to function. So this is equal to this function and plus the odd function, which is this and this. So if we combine these two with an amplitude of 0.5 with an amplitude of 0.5, so if I add these two functions, so this is an even function and this is an odd function of this. So this is my x of t, and this is x of t is equal to half uh, this plus half this. So half of even plus half of odd. Now from the property I know that the, the, the Fourier transform of the even function should be the real part of the Fourier transform of the original function. So this function. So I take this function, this is my x of omega, and I find the real part. I find the real part. And this real part is the Fourier transform of the even function, which is this, or which is this. So now I just need to find the Fourier transform. I just need to find the real part of this. So the real part of this is real of x of omega is equal to real of 1 over a plus j omega. Now what is the real of 1 over a plus j omega? The real part is, to find the real part of any complex number, I just multiply and divide by the conjugate. So I multiply and divide by the complex conjugate. So this is my x of omega, 1 over a plus j omega. So I multiply it by a minus j omega and divide it by a minus j omega. So it will be a minus j omega divided by a square plus omega square. So what is the real part of this? The real part is real of x of omega is equal to a over a square plus omega square. Now this is half of it, right? This is half of the even. So actually, if I write it like that, so half x e of t has the Fourier transform of a divided by a square plus omega square. So x even of t, the Fourier transform will be 2a divided by a square plus omega square. So this is my final result. So this is the Fourier transform of this function. Real. What is the Fourier transform of this function? The Fourier transform of this function, this is not in the question, but we can also find the Fourier transform of this function. So the Fourier transform of this function will be just j omega minus 2 omega divided by a square plus omega square. So in this way we can find the Fourier transform of some functions which have even and odd parts. Okay, now let us go to the next property, which is the property of time differentiation. So I will just go through the properties. We will not do any examples of this property. Uh, so let us look at the property itself. So that is my fourth property. If you have any question, please you can type on the WhatsApp and I can answer from there. So the fourth property is number 4 is time differentiation. Which says omega, if we differentiate x of t, so if on the left hand side we differentiate x of t, so we don't need to find the Fourier transform again. The Fourier transform is just j omega x of omega. That's it. This is my Fourier transform. So this property is used in many occasions when we do circuit analysis. Okay, so in circuit analysis we use this property. Number 5 property is, so for example, so if x of t has a Fourier transform of x of omega, then if we integrate x of t, we don't need to find the Fourier transform again. We can just now from the differentiation, if we differentiate it, we multiply by j omega. So if we integrate it, it will be just divided by j omega. All right. So it will be 1 over j omega x of omega, and plus a constant which is pi x of 0 delta of omega. So this is a constant, and that constant is an impulse of amplitude pi x of 0. Pi x of 0. Now let us look at an example. We need to find the Fourier transform of u of t. What is the Fourier transform? Now we know that u of t is integral of delta. So this is my u of t. So, and I also know that the Fourier transform of delta is 1. So what will be the Fourier transform of u of t? It will be just 1 divided by j omega and plus pi x of 0 delta of omega. Now what is x of 0? X of 0 is actually x of 0 is 1 because this is constant, right? It is always 1. So x of 0 in this case is equal to 1, because 1, it is always 1. So x of 0 will be also 1. So what is the Fourier transform of g of t? It will be 1 over x of omega over j omega. So 1 over j omega plus pi, x of 0 is 1, delta of omega. Now let us go to the next property. Which is the property of time and frequency scaling. So this is a very important property, and in this property we need we we find out the we scale the x of t. So it means that we either compress x of t or expand. So what will happen to the Fourier transform when we compress or expand a function? Yeah, I can just delete this. So that will be my sixth property. Number 6 is the scaling. I will just call it scaling property. And this property says, it's a very interesting property, and I can, and and a lot of applications in communication theory and other branches of electrical engineering. So if x of t has a Fourier transform of x of omega, if x of t has a Fourier transform of x of omega, then if we scale the function, so if we multiply the time axis by at, so if a is larger than 1, it means that we are actually compressing the function, right? We are compressing the function. So on the Fourier side, I scale it in amplitude, but more importantly, I also scale it in the frequency domain. So it means that if we compress a function in time, in frequency it will be expanded. And if we expand the function in time, in frequency it will be compressed. So the Fourier and the time domain and the frequency domain, they act opposite. Expanding the time domain will compress the frequency domain, and compressing the frequency domain will the pulse, the rectangular pulse. So let us look at the rectangular pulse with two different uh, uh, widths. So I have x of t so I have x of t, which is so x of t is given by x of t is given by a rectangular function. So I have two cases. I have from -1 to 1, and in lecture there is it's not numbers, it is variable, but let us just stick to numbers to make it more simple. And the so this is my expanded x of t. So I have this function is rectangular, t divided by tau. So this is my tau, and in this case the tau is 2. And the second function, let us just take it from -2 to +2. So this function is rectangular. Now my tau is double, so it will be rectangular t divided by 2 plus 2, 4. So it is expanded. So in the Fourier transform, we should see a compression according to the property. So let us find the Fourier transform of this first. We know that we know this result that if the if there we have a rectangular function, the Fourier transform is tau sinc pi tau divided by tau divided by so this function is, yeah, omega tau divided by 2 pi. So omega tau divided by 2 pi. And this sinc is, yeah, so this is my sinc function, and I can draw a generalized sinc function here. So if I have a sinc function, and the first zero will be at 2 pi by tau, the second will be at 3 pi by tau, and so on. And the amplitude is tau. So this goes to the tau, this width goes to here, and this also goes to here. Now I have rectangular t by tau. So what is the Fourier transform of this? The Fourier transform is tau sinc, so which is 2 sinc omega tau divided by 2 pi. So omega 2 divided by 2 pi. All right. And the second one will be 4 sinc omega omega 4 divided by 2 pi. So I can either use the property or I can use the direct function. So if I use the property, if I use the property, so x of t is 2 sinc omega tau divided by 2 pi. So if I expand the signal, which means that I divide it, if I multiply it by 2, sorry, I divide it by 2, I'm expanding the signal. If I expanding the signal by twice, so from this equation, 1 over a, so a is 1 over 2 here, a equal to 1 over 2. So from this equation it is this multiplied by 2, so 2 multiplied by a, so it is 2 over a, so a is 1 over 2, so it will be 2 multiplied by 2 sinc omega over a. So this is my omega, so I divide it by 1 over 2, so my result will be omega 4. So omega 2 divided by 2 pi divided by 1 over 2, right? And this 2 will come here, so it will be 4 sinc omega 4 divided by 2 pi. So exactly the same which we got from the formula. So we can apply the property, so we get the same result. Now I can draw this function here. So this function is like this. So the amplitude is tau, which is 2, and the first intersection is 2 pi by tau. And what is 2 pi by tau? Tau is 2, so this will be pi. 2 pi by 2, so this will be pi. And the second one will be 3 pi by tau. So 3 pi by 2. 3 pi by 2. So this will be minus pi. Right? Now this one will be so it will be 2 pi by 4, so it will be pi by 2, the first one, so it will be compressed. So this will be pi by 2 pi by 4, 2 pi by 4, so it will be pi by 2 and minus pi by 2. So as we can see that when we expand the signal in time domain, in frequency domain it is compressed. All right. So this is also this is something which we observe in even in daily life. uh, this is which signal is faster? This is the faster signal or this is the faster signal? We know that this is the faster signal because this comes to 1 0 at faster than the signal. So this is faster. So if I have faster signal in time, I have wide band in frequency. So wide band. If I have slow signal, then I have narrow band in frequency. Narrow band. So faster signal, wide band. Slow signal, fast, slow. Wide in frequency, narrow in frequency. So we know that when we go to a store and buy internet, we want fast signal. So we need higher gigabits per second, which means wideband. If we have slow internet in time, it means that our internet is, the rate is slow. Gigabits per second is slow. So this is what we always, the gigabits is small. So this is what we already always observe, and this comes from this property of the Fourier transform. All right. Okay, now let us go to the seventh property, which will be the last property of today's lecture, and then we can solve a couple of questions from the problem set. So yeah, let us skip this property 7 and let us go to the property number 8, and then we will come back to 7 in the next lecture. So let us skip 7 and go to the frequency shift property, which I feel that it is more important and which comes after this property. So let us first do the 8th property, and then we will come back to 8th in the next lecture, inshallah. So the 8th property is the property of frequency scaling, frequency shifting, and it is it is similar to the time shifting. In time shifting, we said that this was the second property, time shifting. So if we have a function x of t and the Fourier transform of x of omega, if I shift this function in time domain, the frequency domain is multiplied by the phasor t naught, constant phasor. Now in the 8th property is the frequency shift. So in this, we multiply the time domain by so here we multiply the so here when we multiply the frequency domain by exponential, we shift in time. Here when we multiply the time domain by an exponential, we see a shift in frequency. So we see a shift in frequency, omega minus omega naught. So this property is very, very important because the communication theory, EE372, and this property is also called the modulation property. So EE372 starts from this property of modulation. Okay, now let us do one example, and it will clear many things about this property. And that example is when we multiply a function by cosine. So So this is frequent. Okay, so now let us do this example, a very simple example. What is the Fourier transform of uh, example? What is the Fourier transform of, find Fourier transform of x of t cosine omega naught t? Okay. Now we don't know the multiplication. What is the Fourier transform of a function multiplied by cosine? But we do know when we multiply the function by exponential. But we also know that what is a cosine? A cosine is a combination of two exponential, e raised to the power j omega naught t half plus e raised to the power minus j omega naught t half. So I can split this into two and then apply the frequency shift by applying the linearity. So I will just delete this from here, and I put this property here for the reference. So x of t multiplied by e raised to the power j omega naught t is x omega minus omega naught. So I know this property x of t is, so I split it. Whenever I see cosine, I split it. So x of t is, so j omega naught t is x omega minus omega naught, right? I just multiply it by half and multiply by half because this is half, right? Cosine is half. So now I write x of t multiplied by minus j omega naught t. So when I multiply by plus exponential, I get right shift. When I multiply by the minus exponential, I get the left shift, like that. Now when I add these two together, so when I add these two together, x of t is common, so plus minus exponential divided by 2 will be cosine. So when I add them, the answer on the left hand side will be cosine, and answer on the right hand side will be x of omega minus omega naught plus 1 over 2 x of omega plus omega naught. So this property is called the property of, this property is the property of frequency shift, and this property is the property of modulation. Okay. So it means that if we multiply any function by cosine, in the frequency domain, the spectrum shifts to high frequency. So this is what we do in communication. We shift the signal to higher frequencies, and for that reason we need these properties. Now let us go to the problem set number 1, and sorry, problem set related to this uh, Fourier transform, which is, I think, problem set number 4, I believe. So you can, no, 4 is Fourier series, so it is 5. So let us go to the 5 problem set, and let us pick up the first uh, problem, which is problem related to this property. So let us do this problem. So the problem says that this is problem set 5, problem 1. So I need to find the Fourier transform of, so my x of t is equal to e raised to the power minus at u of t cosine omega naught t. All right. So this is the question. Now I can apply this property and easily find the Fourier transform of this. So I know that the Fourier transform of e raised to the power minus at u of t. So in all this question, I split this into plus and minus exponentials. So the first step is always find the Fourier transform of this, the actual function, and then we split the function into two and find the shifted Fourier transform. So the Fourier transform of e raised to minus t, we know this is j omega. The Fourier transform of, now I know that if I multiply it by plus exponential, so plus j omega naught t, and also add multiply by 1 over 2, the Fourier transform of this will be this function shifted to minus this function shifted to omega naught. So 1 over a plus j omega minus omega naught, and there is a 1 over 2 here, so I just keep the 1 over 2 here. All right, and when I multiply it by negative exponential, so when I multiply it by the negative exponential, u of t e raised to power minus j omega naught t, the answer will be 1 over 2 a plus j omega plus omega naught. So I add these two here like I did here. So I add these two, add the two. So on the left hand side I have 1 over 2 e raised to power minus at. When I add these two, I will get the cosine. So 1 over 2 I can just, because 1 over 2 plus 1 over 2 minus will be cosine, and on the right hand side I will get 1 by 2 a plus j omega minus omega naught plus 1 over 2 a plus j omega plus omega naught. So this is the Fourier transform. Now let us actually draw this function. Let us draw this function. So this function e raised to minus at u of t without the shift is this. So this is my time domain x of t. This is my x of omega in frequency domain. So this is like this, a bell curve. And the maximum of this is, when I put omega equal to 0, it is 1 over a. So the maximum is 1 over a. The maximum of this is 1 divided by a. Now when I shift it, when I multiply this by cosine, the function looks like this, as we did before, right? So in frequency domain, we just need to shift this to omega naught. So we just need to shift this to the frequency. Here, this is omega naught, and this is minus omega naught. So in frequency domain, the spectrum, it shifts. And also I have half of it. So this will be half. So this, the amplitude of this will be half, and amplitude of this will be half. So this is my shifted function. So this example tells us that whenever I multiply a signal by a frequency, in frequency domain, I am shifting the whole signal to higher frequencies. And that is exactly what we do in communications. In communication theory, we don't need the signals in lower frequency. When we talk in lower frequency. To transmit this signal over long distances, we need to have this signal transferred to the high frequency. So what we do, we multiply the signal by cosine of high frequency. This frequency is high. Maybe if this frequency is uh, 2 pi multiplied by 1 megahertz, right? So this my signal will go to 2 pi 1 multiplied by 10 raised to the power 6 minus 2 pi multiplied by 1 multiplied by 10 raised to the power 6. So 1 megahertz. So I transferred this signal. If my omega naught is equal to 2 pi 1 megahertz, this one is 1 megahertz, then I transfer the signal to 1 megahertz, very high frequency. In this way, we can put it on radio waves, we can put it on optical fiber, whatever, and we can go take the signals to the long distance. And this is exactly what we do in communication theory. Now let us do the second part of this problem, and then we can stop today's lecture. So the second part is a signal which is multiplied by sine. So I have so same problem, but it is just has a different function there. So I delete all that. So I have this function here. So I have x of t, this is b part. X of t is equal to e raised to the power minus a t, actually minus 3t, and sine 2t. So it's a good example. I have these numbers now. So I don't have variables. I don't have omega naught or anything. I don't have constants. I have enough numbers. So let us do that example. So now I have e raised to the power minus 3t. Let us first write the Fourier transform of this. The Fourier transform of this is, we did it today, it is 2a. So 2 multiplied by 3, which is 6, divided by a square plus omega square. So a square is 9 plus omega square. Because I know that e raised to the power minus at is 2a divided by a square plus omega square. So same thing I apply here, a equal to 3. So 6 divided by 9 plus omega square. Alright. Now I can go, so now sine 2t. What is sine 2t? Sine 2t is equal to e raised to the power, this is omega. Omega naught is 2. So I have e raised to the power j2t minus e raised to the power minus j2t divided by 2j. So I have to multiply this by j2t and then and another one by minus j2t. So what I do here is I multiply it by 3t multiplied by e raised to the power j2t, and also half is there. So I divide it by 2 and multiply it by this. So this will be shifted to omega naught. So I have 6 will become 3 because divided by 2. 9 plus omega minus 2 whole square because it is shifted to 2. The second one will be negative. So I have minus, and I also keep this j here. This j is there. So 3 divided by j because of the sign. And I multiply it by, sorry, this the plus, the first one be plus, the second one will be 3. No, sorry, this is okay. Minus 3t e raised to the power minus j2t. So negative exponential, I have a negative here. Negative 3 divided by j divided by 9 plus omega plus 2 whole square. Now if I add these two, the answer will be sine. So it will be e raised to the power minus 3t sine 2t. And if I add these two, it will be just 3 over j minus 3 over j 9 plus omega 2 whole square. So the final result will be e raised to minus 3t e sine 2t. The Fourier transform will be 3 over j divided by 9 plus omega minus 2 whole square minus 3 over j 9 plus omega minus plus 2 whole square. All right. So in terms of graph, in terms of graph, I have the time domain is this. The frequency domain of this will be just this function, and the maximum is here. It is 6 over 9, which is 3 over 2 over 3 here, because I put omega equal to 0, 6 over 9, which is 2 over 3. Now when I multiply this function by the cosine, sine, so it will be like this. I have this envelope, so as I did before, so it will be like this, multiply by sine. So here I have, this will be shifted to 3 over 9, so half of this, which will be 1 over 3, so this will be shifted to 2 and minus 2, and this will be like this because this is negative. Sorry, on plus side it is, this is plus 2, it is positive, and this side is negative, and the magnitude of this is half of this, so 1 over 3, and this is minus 1 over 3. Or in other words, I put omega equal to 2 here, so this will become 0, and it will be 3 over 9, which is 1 over 3, and similar to here. All right. So we covered today. We covered property number 3, property number 4, property number 5, property number 6, and property number 8, and we did 2 questions from the problem set. All right. I will give you a small assignment from this, inshallah ta'ala, as a homework, uh, and I will give it to you, and that will be contributed towards your final grade. All right, that will be contributed towards your final grade of 40%, because final will be 40%. So we don't know if we have a full final or we can just do it partially. So let us do it. It will be good for you so that you can study it and do an assignment on it. All right, inshallah. So that will be following in a couple of days. All right. Any questions you can send me on WhatsApp, and I can record a video on that question.